Hello everybody! In today's video I'm going to process MLCCs for silver and palladium. I got some MLCCs here, been accumulated from several batches of PCBs. That's quite dirty and not just MLCCs. It is mixed with solder and some other metallic fraction. To be honest, this is the smallest fraction of PCBs coming out while the soldering. That's why I got everything here mix like ICs, tiny IC chips, and you can see some sort of tantalum capacitors. I got another batch. This is quite dirty. As you can see, there are quite a bit of aluminum mix with MLCCs. These are legs of electrolytic capacitors, which is made of aluminum. So if I want to process this for precious metals, definitely that's gonna be a quite hard process, either through a smelting or chemical processing. Also, I try to smelt some MLCCs directly with boric acid as the flux, and here is the slag form, and I managed to get metallic portion out of 10 grams of MLCCs, and I'm going to treat this with nitric acid to be tested for precious metals. Here is another 10 gram sample of this mixed stuff with 2 grams of boric acid as the flux. I'm going to melt this, and I'm going to do that using electric arc. This is what I got. There is a metal bead at the center. I'm going to take that and melt it beforehand before going to process the larger batch.
I'm roasting MLCCs to oxidize solder as much as possible. This process would help in rendering tin and lead oxide into the slag. And there we go, this is roasted material and ready for grinding. That would be much easier now to grind this material. Now they have acceptable particle sizes to be mixed with the flux for smelting. I took 500 grams of ground material and mixed it with 85 grams of silica sand powder as the flux. You can either use boric acid or silica sand. Then I place the mixture into my handmade melting dish, which I built by cutting a bowl-shaped hole into the fire break using a handmade tool. I attempted to fuse the mixture using charcoal. To ensure everything melted properly, I needed to heat it up to 1200 degrees Celsius. At first glance, it appeared completely melted to me. However, upon breaking melting dish, I observed that the only top of the charge was properly subjected to the heat. This time I decided to do the process using a oxypropane torch. I persist in smelting to obtain a 100% metal fraction from the capacitors. Of course, you can treat this material directly with acid, but before that you need to grind it into a very fine powder using a ball mill. I managed to smelt the charge easily with the oxypropane torch. After cooling, I hammered it to get the metal alloy out. Here's the nice metal bottom and really dense slag. So about 20% of the weight of ceramic capacitors is composed of metals. Now the game has begun. It's time to refine the metal alloy into the pure silver and palladium. To start refining, 90 milliliters of nitric acid added to digest the alloy. Dissolving that alloy in nitric acid was quite challenging. To achieve it, I had to maintain the temperature near boiling. About 250 milliliters of 65% nitric acid was used to fully digest the alloy. I noticed some precipitate at the bottom of the solution, which seems to be methacetonic acid resulting from the reaction of tin in the alloy with nitric acid. Before processing for palladium, I'm going to precipitate silver as silver chloride. I let the solution sit overnight, then filter it to begin precipitating palladium. Now I'm going to precipitate palladium in a unique way. I'm going to attempt precipitating palladium as palladium carbide. Before that, I added some sulfuric acid to remove lead, and then I denoxed the solution using sulfamic acid. The solution was filtered once again. To precipitate palladium carbide, you need to reduce the 4 plus charge palladium ion in the solution to the 2 plus charge. To do so, I added some sodium metabisulfite. The solution is ready to precipitate palladium. I use calcium carbide to generate acetylene gas, which reacts with palladium to form palladium carbide. Calcium carbide is easily accessible. To enhance the reaction, I dissolve acetylene gas in nail polish remover or acetone. Then I added acetone in several portions to the palladium solution. To dissolve the gas into the acetone, I used a mason jar to build up pressure. Copper and silver carbide are energetic materials, but copper won't precipitate as carbide in an acidic solution. You just need to fully precipitate silver chloride prior to this process, as I did. Heating the solution to 50 degrees Celsius could accelerate the carbide formation. You can also bubble acetylene gas directly through the palladium solution. I did this to precipitate the last bit of palladium. Or you can simply add more gas solution in acetone to the palladium solution. This should be continued until the bubbles become colorless in the solution. You may wonder why the solution color is still brown. Let me show you why. Copper in interaction with dissolved acetylene gas makes the solution brown. This can easily be fixed by adding some hydrogen peroxide. Now let's test for the presence of dominant base metals. I use ammonia for copper and a 1% dimethyl glyoxime solution for the nickel. A blue solution after the addition of ammonia indicates that the copper is still present in the solution, while the pink color after addition of DMG shows the presence of nickel. The reason I didn't use DMG in the first place to precipitate palladium is that I was looking for a cheaper alternative. The filter paper has been washed and dried, and now it's time to calcinate it to convert the palladium carbide into the palladium black. I also recovered silver from silver chloride using lye and sugar. I transferred the silver powder into a crucible to melt it in the propane furnace, while on the top of furnace the palladium carbide calcination was carried out. Alright, this project is done. I hope you enjoyed this long video and found it useful. Please don't forget to subscribe and hit that like button. Till next project, see you next time.